What's up, everybody? It's Dan from SageMathTutoring.com. It's going to be SageMathTestPrep.com soon, but not yet. Here's the new logo, though. A little preview. It is a triangle. Same triangle as before, only the colors are better. So anyway, this is a video for a particular student of mine who's doing really well. It's got some momentum. And however, there were two problems that kind of stuck out that I would like to go over with him. And hopefully, as usual, it will benefit the rest of you fine people watching. So in the figure below, BD is parallel to AE. What is the length of CE? So BD is parallel to AE, therefore that line is parallel to that line. Quick review of parallel lines. Anytime you have a parallel line and it's cut by a transversal, it is the case that the sharp acute angles are equal to each other. And that actually includes these guys, right? So that's nice to know, okay? It's also the case that the larger obtuse angles are equal to each other. There's a fancy name for these. They're called corresponding angles. A lot of you students at home might be a little bit more used to the parallel lines being horizontal and then having an obnoxious transversal just cutting across like that. In this case, the parallel lines are vertical. So you do have to sort of be mentally flexible with your perception of the parallel lines with the transversal. But nonetheless, it's indeed true that these are equal to each other. It's also true that, if you had something going straight across like that, or even, actually I should say like this, and maybe even such a way that's perpendicular, well, this one would be perpendicular as well, okay? For the exact same reasons, these are corresponding angles, okay? Now, it might be the case that you have to temporarily, like when looking at this yellow line with the blue parallel lines, you have to temporarily ignore the green one to just really focus and see that these are corresponding. When you're focusing on the green transversal with the two blue parallel lines, you might have to temporarily ignore this yellow one, really focus here to get clear on the fact that these are corresponding angles. In other words, to avoid confusion, especially when there's more than one transversal, you might have to have selective tunnel vision to really focus on one transversal at a time. Now, the reason why I bring all this up is because that is exactly what's happening here. The bottom line is we know for sure that these two blue lines are parallel, right? And we also know that this is a transversal, right? Which means that that angle is the same as that angle, okay? So that was a big, disgusting mess, okay? But hopefully that makes sense. You can rewind it if need be. And there we have that, right? Now we also know that for the exact same reason that these are corresponding, then we know that these are corresponding. So this is 90, sure, great, but this is 90 also. All right, so that's important. Now why that's important will be revealed soon, okay? But the bottom line is, as soon as you know, parallel lines, transversal, blah, 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 start labeling the crap out of the diagram. Start making very clear to yourself what angles are equal, what angles are, related to each other. So anyway, that's the deal with the angle situation. And at the end of the day, we're trying to find CE. So I'll actually just darken that. We want to find this at the end of the day. Now, the question is, like how are we going to do that, of course? Well, there's another concept called similar triangles, where it's like if I have a triangle like that, and they're like different sizes, but they are like the same shape, and if you know for a fact that this angle is equal to that angle, this angle is equal to that angle, and this angle is equal to that angle, well then these triangles are similar, and when you have similar triangles, these side lengths are proportional. So for example, if that's 3 and that's 6, let's say that this one is 5. Well, we know for a fact that this one has to be 10. And the reason for that is because 3 times 2 gives me 6, and these sides are related. Because this side is the side between the blue and the green angle. This is the side that's between the blue and the green angle. So these two sides are related. And 3 times 2 gives me 6. 5 times 2 gives me 10, right? So that's one way of going about it. The other way of going about it is, let's say we didn't know that it was 10, the more sort of textbook way. The way that I'm about to talk about right now is the way that will work under any circumstance. So you could also set up 3 over 5, which has to do with the two known side lengths of that one. And you literally would just set that equal to, if that's x, it would be 6 over x. And then you would cross multiply. 3 times x is 3x, 6 times 5 is 30, 3x equals 30, so clearly x equals 10, right? You could divide both sides by 3. I'm not going to do that right now, but you would just cross multiply and solve for x, and you would get 10. Okay, so that's nice to know. So there's at least 2 ways of figuring out what x is. One is to, if it's obvious, if it's 3 times 2 equals 6, therefore 5 times 2 equals 10, then go ahead and do that. If it's not obvious, imagine that's a 3 and that's a 4. That might not be obvious because 3 times what gives you 4. So that's not as obvious, but you could always set up the proportion. 3 over 5 equals 4 over x, and then you would take it from there. So anyway, that is a brief review of similar triangles and how the side lengths are proportional. Once again, how do you know when similar triangles are similar? You know that triangles are similar when the angle measures are the same. Well, that's exactly what we have going on here, right? We totally have that going on here. So we're going to tease these triangles apart and really analyze them. Before I do that, though, I do want to throw in another quick concept called the Pythagorean Theorem. It is the case that when you have a right triangle and the 90-degree angle is right here, the longest side length is always going to be the one across from the 90 degrees. Typically, we call that C. That is also called the hypotenuse. It is the case with literally every, right triangle that A squared, the length of that leg, plus B squared, the length of that leg, squared, equals the hypotenuse squared. And you could always use that equation to figure out, what a missing side length is. Now, I do want to also draw your attention to the fact that there are famous right triangles. For example, there's a famous right triangle called the 3, 4, 5 triangle that sort of spares you from having to do the Pythagorean theorem. Now, you could always double check. You'd be like, is it true that 3 squared plus 4 squared equals 5 squared? Well, if you were to test that, you would indeed see that it's true. But the real strength of the 3, 4, 5 triangle is that it's not really 3, 4, 5. It's really 3 times some number, 4 times the same number, and 5 times the same number. What do I mean by that? Well, the bottom line is if you had something that was like 27, 45, and then you wanted to find B, well, this is 3 times 9. This is 5 times 9. So this is going to be 4 times 9, and that is going to be 36. All right. So a better way, perhaps, of thinking about it is 3x, 4x, 5x. It just so happened that the x in this case was 9. But so it's 3 times 9 gives me 27. 4 times that same number 9 gives me 36. 5 times that same number 9 gives me 45. So the x is 9 in this case. All right. But most, math textbooks will just have it as 3, 4, 5. Okay. But keep it in mind, it could be like this. It could be a similar version like that. So anyway, that's a whole bunch of information, okay? But that's arguably maybe why this would be considered a relatively hard problem, or at least a problem that's like a little bit towards the end of the math section, because it features so many different concepts kind of crammed into one single problem. Nonetheless, our goal is still to find CE. What we're going to do is we're going to tease apart the triangles. Now, you don't have to do this, but a lot of people do find it to be helpful to actually separate the small triangle from the huge large triangle. So we're going to do that. Okay, and that's 90. Now this is C, E, A. All right, and we will erase stuff. Okay, so labeling the small triangle would give us 8, 6, and that's all we have. And then labeling the large triangle, well, we don't have much to go on. We don't really know what CA is, right? Here's CA. We don't really know what that is. We do know what EA is. That's certainly 18 for sure. And yeah, so that's that. I mean, at the end of the day, we are, again, trying to find that one. That's literally the answer. The answer is whatever this length is. Well, I'll tell you what. I could totally see that it's like these are proportional triangles or similar triangles, because it's definitely true that, angle C is equal to itself, right? C is equal to itself. But it's also true, we already established that D is equal to E because of the whole transversal shenanigans. So D is equal to E, like the measure of the angle. And we also know that angle DBC, this guy, that's equal to, that's equal to this one. So since it's yellow in the above diagram, we'll make it yellow here, yellow, and actually we'll make this black. That's black, and that's black. Okay, so this angle is equal to that angle, this angle is equal to that angle, this angle is equal to that angle. So I'll tell you what, these are definitely similar, and because the angles are the same. Remember how I said that's literally all you need to know that triangles are similar. It's if the angles are the same, and if the triangles are similar, then the side lengths are proportional, right? Now we're trying to find this one, so it'd be nice to know DC. And in fact, I can already see, I'm not going to bother with the proportion. 6 times 3 gives me 18. So something, this times 3 is going to give me that. So if I could just find this, that would be awesome, right? So let's find this. Well, you might notice this is divisible by 3. This is divisible by 4. So this might be a 3, 4, 5 triangle. So let's just inspect it. 3 times 2 would give me 6. And it is the case, luckily, that 4 times 2 would give me 8. So already we have a 3, we have a 4, so we know that 5 times 2 is going to give me this one, so that's 10. It turns out that the small triangle is a 3, 4, and 5 triangle, because 3 times a number gives me 6, 4 times that same number gives me this side length, and 5 times that same number gives me 10. Notice how all we needed were the 2 legs in order to make that conclusion. The fact that we knew that this leg was 6 and this leg was 8 was literally all we needed to know that it was a 3, 4, 5 triangle. Okay? Now, 3, 4, 5 does not apply to regular triangles that look like that. 3, 4, 5 only applies to, right triangles. So, anyway, I think we all see where this is going. Clearly, 6 times 3 gives me this 18, so 10 times 3 is going to give me 30, and that is the answer. Moving on. So this problem right here is a classic mixture problem, which I find is a particular kind of algebra word problem that teachers don't spend a lot of time on. So anyway, we are going to show, or I'm going to show you guys the best way to solve these problems ever. There's also other kinds of algebra problems like work problems and so on that can trip people up. Maybe I should do a whole video series on that. But anyway, how many liters of a 25% saline solution must be added to 3 liters of a 10% saline solution to obtain a 15% saline solution? So honestly, that's going to be confusing as heck if you don't know what to do. So here's the bottom line. The truth of the matter is the first mixture, plus the second mixture equals the total mixture. Okay, so I hope that's a nice looking sort of diagram to look at. And it's honestly speaking the obvious. I know it's speaking the obvious. First mixture plus second mixture equals the total mixture. But honestly, it's good to just get a view from 100,000 feet and sort of take it from there. All right. Now, you could draw this. You don't have to write this, right? But you could draw this. And at the very least, if you draw these big O's or whatever, these big circles, it'll remind you of, the reality of what's happening in the problem. And what you really want to do is, in a way, you need to prepare to write 3 things vertically. 3 things vertically in each of these. We're going to start with the top thing. The top thing is always going to be the percentages. So the percentage is 25% in the first mixture. And it's going to be, what is it in the second mixture? Looks like it's 10%. 10% in the second mixture. And then in the final mixture, we're trying to obtain a final mixture of 15%. So we're going to have 15% there. So the percentage of solution in the mixture goes on top. And then underneath, you could write something else that has to do with the actual quantity of liquid or whatever, the actual quantity, like the volume or whatever. So it's like, how many liters of this solution? Well, that's X. So we don't know how many liters. So this is X in terms of quantity, right? And under here, it's going to be 3 liters. And then under here, we must be added to 3 liters to obtain a 15%. So we actually don't know how many liters, but we know that it's going to be X plus 3, right? So that's huge. You really need to see that. That, the volume of whatever the first mixture is, plus the volume of the second mixture, well, that's going to give us the total volume over here, and that's X plus 3. Okay? So that's what you need to do. All right? Percentages across the top, volume underneath. Remember, if you don't know what this is, well, you actually do. It's X plus 3. Okay? Then get ready to be happy. It's the most beautiful thing ever. You draw this beautiful rainbow. And this really is the rainbow that highlights, what the equation will be. And what is the equation? Well, it's going to be this times that. But we want to write that 25% as a decimal. So it's going to be 0.25 times X, right? And then over here, it's going to be 0.10, 0.1 really. 0.1 times 3. Just put the 3 in parentheses. And then over here, it's going to be 0.15 times X plus 3. So over here, it's going to be 0.15 times the entire quantity of X plus 3. All right, so that really shows it's this bottom part that shows what the equation is going to be. So that's going to be 0.25x plus whatever 0.1, I'll put that in parentheses too, times 3 is, which we'll work that out later. And that's going to be 0.15 times X plus 3. Now here's the thing. We could totally just be like 0.1 times 3 and figure all that out and distribute this. But to me, I don't like decimals. So I'm going to multiply everything by 100. And when I multiply everything by 100, that's going to distribute here. That's going to distribute to this clump. And that's going to distribute to this. Now, when it distributes here, what does the 100 do? It brings over the decimal two places to the right. So that becomes 25x. Now, when it distributes here, you need to understand that 100 only gets multiplied to one of these numbers, but not both. So I'm going to choose this 100 to get multiplied to that. So it becomes 10. So this becomes literally 10 times 3. Now, if you're a little worried about that move and wondering why didn't the 3 get multiplied by 100, I'll explain that after. But just take my word for it for now. This 100 only multiplies to one of these things. Then, the 100, when it gets multiplied all the way to this guy, that moves that over. It doesn't affect this, though, for the same reason that the 3 was not affected. The x plus 3 will not be affected. When we multiply 100 times this entire clump right here, it only affects the 0.15. So this becomes 15 times x plus 3. Now I'm doing that to avoid decimal confusion land. So we still have 25x. 10 times 3 is easy. That's just 30. And then it's going to be 15x plus 45. Then, let's see, what do we got? Well, let's subtract 15x from both sides, and we'll subtract 30 from both sides. And we'll just kind of do that all at the same time. And what that's going to result in is 10x equals 15. Dividing both sides by 10 gives me 15 over 10, aka 3 halves. Okay, so x is equal to 3 halves, aka, was that 1.5? All right, so that is 1.5. Okay, so x is 1.5. And honestly, that's what they're looking for. How many liters of the 25% solution? That needs to be 1.5. Hopefully that works for you. I do want to explain what happened when we multiplied that 100 times this term, or you could even think of 100 times this term. I think I'll focus on 100 times this term because there's more to say about that, and when you understand this, you'll automatically understand that. So let's cover what happened when we multiply 100 times this term. So once again, there's probably a question, or there might be a question like, okay, I multiply 100 times the whole equation in order to move the decimal places over. But again, when you multiply 100 times this and 100 times this, it's like, why didn't we multiply 100 times x plus 3? Well, I'm going to illustrate that with sort of a separate but simpler situation. Let's be very clear. If you multiply 3 times 4 plus x, well, we know that you distribute the 3, okay? And that becomes 12 plus 3x. But if we were to multiply 3 times 4x, I think everyone knows intuitively, or just due to practice, that that's 12x. Because the truth of the matter is, this is really just a string of 3 numbers being multiplied together. Regardless of how it was originally written, if they're smushed up next to each other, that's just multiplication. It's a whole string of, it's like a multiplication train, basically. Whereas this is addition, right? So this is such that it doesn't matter what you multiply 3 times first. You might as well just multiply 3 times 4, because that's something that can be simplified. Whereas x, we don't know what it is, so x just remains x. Okay? Now, in the exact same way that you have just, a string of 3 numbers, I'll write the original situation. Imagine you're multiplying 3 times 4x. This is secretly just a string of 3 numbers. If you have to look at that and then look at this a bunch of times, go ahead. This is clearly a different situation than this, right? This is where you do distribute, and you don't distribute here. Over here, it's the same thing. When I multiplied 100 times this, let's just focus on that. I'll keep the 100 in green. 100 times, 0.15 times x plus 3. Right? Because that's kind of what happened. It was 100 times this whole thing. So it's 100 times this whole thing. Well, think about it. This is just a string of 3 numbers being multiplied together. It's 100 times 0.15 times x plus 3. It's just a string of 3 numbers being multiplied together. And what that means is, in the same way that we multiply the 3 times the 4 to get the 12x, we only multiply the 100 times the 0.15 to get the 15 times whatever the heck this is. Okay? So this only multiplies to that for the exact same reason that this 3 only multiplies to the 4. And yet the x remains untouched. And yet this remains untouched. Why are we leaving x untouched? Because we don't know what it is. We have to leave it that way. Why are we leaving x plus 3 untouched? Because we don't know what it is. We have to leave it that way. Okay? So that was potentially long-winded. But I'd rather be thorough than not explain enough. Hopefully that makes sense. But yes, the answer is most definitely 3/2. This would be a grid-in question, as with the last one, I believe. So for the last one, you have to write in 30 in the grid-in response. For this one, you could either write 1.5 or 3/2. Both would work. Anyway, I hope that's helpful, and I will see you guys later.